And what you need to do is I'm going to come over here and draw the equivalent circuit for this guy right here. I'm going to come over here. I've got this, R2, which I don't know. I've got this. I do know a lot of stuff about that. I know it's 1.5 volts at 15 milliamps. That's what I know. And then this goes to common because the transistor is going to saturate. When the transistor saturates, it acts like a water closed switch. I've got 15 volts right there. So this would be back in DC. Back in DC, if I had to draw this circuit right here, they said, okay, I'm going to draw this as a resistor. This is going to draw 1.5 volts at 15 milliamps. I've got a common right there. I'm going to put 15 volts right there. What size would be R1 up there, or the resistor up there? You'd say, well, Kirchhoff's law says, well, this sucker's got to drop 15 volts in a series loop, or a series loop. Okay, that's a series loop. A loop means current flows in a loop through there, right? You understand? So how much voltage is being dropped by this resistor right here? If Kirchhoff's voltage law says the sums of the voltage drops have to equal to the applied voltage. Not can, it has to, right? You understand? That's a law. That's a law of physics. So what voltage is going to be dropped up? What voltage is going to be dropped right there? Huh? 13.5. So this guy right here's got to drop 13.5. I've given you the current flow through the diode. What's the other law? It says the current is the same throughout a series circuit, right? You understand? So I know this resistor right here's got to drop what? So R2 is going to drop 13.5 volts. Ohm's law says R is equal to V over I. So I'd come over here and say 15 milli. And then I'm going to calculate the calculated size for R. Y'all understand that? And what's the calc? What's that? I gave it to you. So what do we come up with the calculated size for R2? Here's our 900 ohm resistor out there. So so did this calculate to be 900 ohms exactly?
That was the part that I got right on that one. Definitely. I got that part right.
Okay, so here, what did we choose?
You're going to choose 9, like you came to 910.
And what's the power? I square R, you can use V times I, right? Here's, so 910. Of course, we would probably have to recalculate the current to be exactly right, but this is going to be so I need to add that to my worksheet too, because a lot of people don't understand that. When they go for a 100 ohm resistor, they think each 100 ohm resistor is the same, right? Okay, 910 ohms. Okay, now I know this guy over here. I know the voltage drop across this guy right here. I know the voltage drop right here. It's 0.7. Here's the second series loop right here. So if that guy right there is dropping 4.7, then I know this guy right here has got to drop 4.3. I know, right? Because of Kirchhoff's voltage law. But I need one more thing. I need I. I know I in the collector, but I don't know I in the base yet. But I do know that this thing called beta is equal to IC over IB. So that's the new formula that we got to pick up in saturated switches or in bipolar transistors. So you got to understand that beta. That beta is the current gain of the transformer. So this is how much current I put on the base compared to how much current I get out of the collector. So what beta so I need to solve for IB. So I could take this thing and I could put it in my little wheel, right? So beta, and then I could come over here and do this little thing, and I could say IC, IB, and I want to solve for IB. So what's IB going to be equal to? Well, IB is going to be equal to what? Beta. Yeah. So IB is going to be equal to IC over beta. So I've got beta. So this is another thing we got to know about saturated switches. I've got a beta that could be anywhere between 75 and 300. I want to make sure this thing saturates, so we're going to use minimum beta. So then IB, and this is saturated, is going to equal to 15 milliamps divided by 75. Everybody understand where we got that at? So this beta is guaranteed, this beta is not. And what example did I use? Minimum wage. So if you legally go to work in the state of Alabama, they got to pay you at least what? Minimum wage is what? Guaranteed. $300 an hour is not. Even that's not what I made. It'd be nice, wouldn't it? So R is equal to V over I. So RB, whatever it is equal to 4.3 divided by whatever this comes up and gives me. I didn't do the math. So what do we get for IB? Something microamps, yeah, but what is it? You got it? Huh? .3 or 198 micro would be equal to the base resistor, which is R1. You got your worksheet, Alex? Round out to the next standard AEO. So I'm using like 198 microamps to control 15 milliamps. So I'll put a 0 over here. The transistor, we have no base current. If you have no base current, we have no collector current. Transistor cuts off and the diode goes off. So what size are we going to use for RB or R1, excuse me? That's how much it drops, right? These are microamps, yeah, on the base. And how did we get the base current? We used the Beta formula. That's what size we're going to use. Wait. $21.71. Kilo ohms? Yeah, you gotta get that right. Just, in electronics, you just can't say 21.7, right? Of course, what we're going to do here, we're going to round down. But we got to assure saturation to the next standard value. So what would we use there? Was that 20K? And that's what you got to understand, guys. I'm using 198 microamps to control 15 milliamps. So this guy is a current to control current. A very small base current controls the proportionally larger collector current. Okay, we okay. So the next one is basically the same. Here we give you a light bulb that's rated at 12 volts. So the problem we have here is your LED's only rated at about 1.5 to 2 volts. We use 1.5 to 2 volts if I don't have the data sheets. If I got the data sheets, of course, I would use that. And about 15 milliamps on these. If you're a little higher or a little low, it doesn't make any difference. On your LEDs, if you choose an R2 that's a little lower, then the LED will be a little brighter. If you choose one that's a little higher. So here, since this guy drops, and we assume the transistor's dropping 0 when we saturate, right? We assume when it cuts it off, it's dropping the entire voltage. When we turn it on or saturate it, it's dropping 0, even though it's not. It's going to be, when we look at the data sheets, we'll see it's got a saturated current, but it's always going to be less than 1 volt. So we assume it's a 0. So if my load is dropping less than what I've got up here, then you'll have to use a series dropping resistor. If it's rated at the same, like light bulbs, there's all types of 12 volt light bulbs out there. That's what your car light bulbs are rated at, right? So here we don't have to have a series dropping resistor, but we do have a light bulb that's rated at 12 volts, and then it's rated at, so the light bulbs are rated in watts and volts. I don't need watts. I need amps. So what I'm going to have to do is I'm going to have to transpose my formula where power is equal to V times I. I'm going to have to transform this to solve for I. So what would I be equal to if I transpose it? Well, let's put the formula right. P over V, right? Let's do the formula first. We just transpose that. So IC, saturation IC, would be equal to 150 milli divided by 12. Now you think about some of your light bulbs you run in your car fills with a pretty good deal of current, especially your like you got floodlights or you got headlights. Okay, so now we got IC is equal to 12.5 milli, and I'm going to turn this on with 12 volts. So I know this guy here is going to drop 11.3 volts. So the base, the amount of current that's going to be required to saturate this thing is going to be equal to 12.5 milli divided by 50. Okay. So this is why we can turn on our headlights with a little push button on our, right? You understand that? Our little turner, mine's got a little knob. There ain't no way in the world I could control my headlights through what? Through that little old thing you got on your steering wheel. But we could run it in your engine, in your body control module. There's a bunch of transistors out there, right? You understand that? Where I can put microamps into that little transistor. Now I can control the headlights and all kinds of stuff. So now I know my IB. So R1 would be equal to the amount of voltage it's going to drop divided by 250 micro, and this would give me a resistor, and we'll go down with the next standard value here. So what's R1 equal to? What's that? Everybody okay there? So what are we doing? We're just using laws. Basically, there's only one new formula that we look here, right? That's this. Okay, this guy. This is a relay, so we can have anything over here. Huh? So this is a relay. This is the international symbol for a relay, by the way. In motor controls, you'll just use this symbol right here. Y'all understand a relay? Yes or no? Huh?
No.
Relays are what actually moved us into automated manufacturing. So if I want you to come over here and I tell you to turn on that light over there, somebody's going to have to get up off their butt and go over there and do what? Flip the switch. It would be nice, but now if we want to turn on our TV, you don't get so. When I was a kid, if you wanted to turn on the TV, you had to do what? You had to get up and turn it off, right? If you want to change channels, you had to do that. But now we got a little remote, we can just hit a little button and turn on our TV. Well, how do we do that? Well, relays are electrically controlled switches. I think I've got one in here somewhere. I'll have to show it to you. But what we do is we take a huh? Yeah, but I got it. Here you go. Here's the key. So what we do, we know when we put current through, and I'll have to go find my demonstration stuff, but I'll show you all this later. I know when we put current through a conductor, it generates a magnetic field, right? Everybody understand that, right? Everybody okay there? Then if I take that and I wrap it like this, then each little magnetic field, if we wrap it really tight, each magnetic field combines with the next one to it. And then if we come over here and we put a chunk of metal through that, metal concentrates magnetic fields. Right? You understand that? Okay. All right. So I'll have to show, but what if we came over here now, and then I put a, let's do it like this. So let's put a switch right there. It's got metal on it. Then I come over here and I put power across this, it generates a magnetic field, it will automatically close that switch. If I turn the power off, if this has got a spring on it, then it would do what? It would automatically off. This is a relay. So a relay is an electrically controlled switch. So we have some of your contacts are normally closed. So these are drawn below. So normally closed would do what? They would open. And then normally open would do what? Close. When we put it. So now we have an electrically controlled switch. Now we can automate things because now it's taking it away from what? Me deciding when circuits are turned off and on. over to now electrical control when it turns off. So I've got a switch back there. It's a little old tiny switch on the wall that we keep covered up that I can kill power in this whole room right here. You think one little old light switch is going to be able to control all the power in this room? No. Well, what does it control? A relay. You can actually hear it click. By the way, I'm not going to show y'all where it's at. Because people, when they see switches on the wall, what do they have a tendency to do? Stephen Wright, he used to be one of my favorite comedians. He said he moved into a new house, and there was a switch on the wall, and he'd just go by and flip it and flip it and flip it, and one day his neighbor called and said, cut that out. So we have a tendency. He's really funny. He said somebody broke into my house and stole all of my furniture and replaced it with exact replicas. So, go ahead, Stephen Wright had put that in for a long time. So we keep it covered up because I'd be at home and I'd try to remote in and everything would be dead and I'd have to come back into Canvas and somebody had tripped the relay. So this is the coil right here, and this is showing you the switch that is being controlled, the actual switch that's being controlled by it. So over here, I would come over here and I might have, up here, this might be 120 volts, and this might be 120 volts AC. And then down here, over here, I've got a light bulb. So what I'm doing here is I'm doing what? I should have drawn a... So now I'm controlling 120 volts with DC. And that's another real nice thing about relays. The contacts and the coil can be completely isolated from each other. So it means I can control this relay over here, and I could be controlling DC on one side, AC on one other side. I could have AC relays.
Is that how emergency switches work in certain components?
What's that?
Let's say you got like a machine, you got to turn this on, turn that on, for like these can work together. So if I push the emergency switch, it's going to be like a relay and turn all that on.
Turns off everything. Yeah, the e-stop button. Yeah, very simple. Most of your e-stop buttons are controlled by. This would be the e-stop. And then we put our relay over here. So what we do is this right here would be, this would start everything, right? So usually when you pull out an e-stop or hit an e-stop, when you pull it out, you still got to hit another button, right? And then this right here would be the e-stop. And then this right here would be main or something like that, and this would be the symbol of a contact being controlled by this relay. We just give them the same name. So I press this button, touches it, brings in M. M comes over here, closes, and it seals itself in. And then if I hit the E-stop, what happens? Everything drops out. And then down here, we would have all these contacts down here being controlled by what? M. So you hit E-stop, and this guy here might be running a motor, this guy here might be running, and then everything drops out. So this is a pretty standard e-stop switch. Pretty standard.
So the interview for jobs, you would be surprised how often they ask people to draw
Start. Yeah, start, stop. A start-stop relay control circuit is probably the most widely used circuit. Robots, they don't use it. They use an e-stop controller that's inside the robot, which is pretty neat. But yeah, this is the standard start-stop station. We can use this to stop the motor, start. But instead of using switches, all the guy has to do, or person has to do, is just hit a push button. In industry, you're not going to see a lot of switches. You're going to see a lot of push buttons. They're going to be real big, so people can hit them with gloves on. So this is a relay. This is we call this a counter EMF, and I'll show y'all this in a minute. The problem we have with a lot of turns of wire, this creates a device called an inductor. So if I put AC on this thing wouldn't work at all. So we have DC relays and AC relays, guys, and they are not interchangeable. So if you put an AC relay on a DC circuit, you're going to burn up a bunch of stuff. If you put a DC relay in an AC circuit, you won't create a magnetic field enough to pull it in. So we know this guy right here needs 6 volts. And by the way, relays are usually rated in volts and ohms. DC relays, sometimes they don't give you the ohms because they know you can take your ohm meter and do what? Just measure across the board. So now we know this guy right here, I'm putting 12 volts up here. I need 6 volts right here at 375 ohms. So what do I need to do? And I can't get to my razor. So let me exit, discard, and bring it back up. My recording software is covering my oops. So what do I know? I know I got 6 volts, 375 ohms. That gives us our current, right? So my collector current is going to be equal to 6 volts divided by 375 ohms. Everybody okay with that? So I understand that. Yeah, so this is the rating of the relay right there. It's a 6 volt relay, 275 ohms. We had this exact problem. We had a little peanut relay. It was rated at 12 volts. It was rated at 24 volts, and it didn't have the ohm rating on it. We measured it with our ohm meter, and we was putting this on 120 volt circuit. So this is our series circuit. This is the series circuit over here. There'll be no current flow through the diode. Why is there no current flow through the diode? Well, the cathode is pointing toward the plus, and the anode is pointing toward the minus. So this guy here is reverse bias. So there's no current flow through the diode, except for what we call
I did instead of like 12. I did the 12 volts over the current, and then I'm now seeing the answer was supposed to be the 6 volts.
Yeah, because I don't know this, right? You understand? I do know all I need to know about that.
Yeah.
Right? And I know it's series. I know the diode has nothing to do with this thing right now because it's reverse bias. Are we okay? Are we okay? So IC would be equal to 6 over 375 ohms. So what's my IC got to be to bring in this relay? So I know I want R1 to drop 6 volts at 16 milliamps. Are we okay? Yes, sir.
On this TV, you got 9.9 over 360. The 5.9, but I see that it can be just 6. Due to the reverse bias, the 6 volts is going to go back up, and those 12 minus the 6 volts because it's dropping that 6 kind of. That's the part that kind of got me confused too. Like the 12, it's plus 12 at the very top, R1. We just calculate, the 6 volts due to the fact that it's the reverse bias is going to drop that, and that's kind of the reason that 6 volts over that 16
right now you need to just ignore the done. So it's just reverse bias.
Gotcha.
So you're right, it should have been 6 votes, Janice, I'm sorry. But it's not gonna change the size of the resistor. So I need to make that correction. I don't know where I came up with 5.9. Actually, it should probably get a little higher than 5.9. Are we okay? That's a good point.
Oh, this is a side question. With the plus, with the battery facing up, and we got.
This is not a battery, this is a relay coil.
That's
Yeah, and that's what I talked about. This is the symbol for this coil of wire right there. This is what we call the international standard symbol. And over here we use what we call ANSI signals, which is the national standard. So if you do take motor control, which is a really good class, this symbol and this symbol are the same. So this is the international standard. So you need to know both of these. This is ANSI. Now, American National Standard Institute. So how many people in the world are going to use that term? Not many, right? So they redid and did what we call an ISO symbol, which is a Mikey symbol that would be. And this is the only symbol I had in my schematic drawing software package, which is that is not a battery. What's a symbol for a battery? This is a world. This is a symbol of a DC voltage source. So is that okay? That makes sense. So that's the relay coil. That's what that is. You got your worksheet, Tom? So why do we come up with R1? What's the calculated value?
375.
What, 375? We don't have one of those, so we'll round it. Keith, though. Okay? Very okay. So what size did we choose? 360? Okay. So 360. Then I'm going to take, here's beta. I'm going to use 30. So I'm going to take our 16 milliamps. I'm going to divide it by 30. And that gives me IB 16. So what's our saturated base current?
Yeah, you're gonna get 533 milliamps.
I can't take 16 and divide it by 30 and come up with
16 milliamps, right?
16 million.
Yeah, 16 e to the negative 3 divided by 30 will give me 5.33 e to the negative 4. We take that over. So that'll actually 53 milli.
Y'all need to understand when you know your answer's got to be wrong. I can't take 16 and divide it by 30 and come up with an answer that's bigger than what I started off with, right?
We got to do our HASI saturated
ICSat, we was given that right here. We cut, that's ICSat. You understand, Mario?
I do.
I got a question about the R1. You rounded down from 375 almost to 360. I thought on the collector side you always rounded up.
No, you round.
Other way.
No, you round. So what is up and what is down? I mean, so 375. So what's the next one up from there?
Next one, 375, 390.
390. And what's the next one down from 375?
360.
Okay. So one is a difference of 15 ohms, right? And the other one is a difference of what? I could do, 390 minus, 15. So you're right, Lee. Here, don't make every switch when you can. Well, all we have to do is guarantee that we have enough pulling current for the relay. So
How would you decide which one to use in this situation? Would you go with the lower one or the higher one?
I would use, and I did this to the lower one because I know if we lower the current on the relay, we might not have enough current to pull it in. That's a really good question. I didn't know that was exactly the same.
6 volts and 360, they're getting 16 milliamps.
So 390, if we use the 390, then this guy here needs 16 milliamps to pull it in. If we use the 390, then it's going to drop more than, I can't get to my 19. That's in my pause thing down here. Is that on top of my where I do my pins? I can do it with so a relay has what we call a pull-in current, which is the minimum amount of current you can put through the relay that guarantees that it will generate a field big enough to pull it in. So undoubtedly, that's what I was looking at when I rounded down. But what happens with the relay? The purpose of the diode is what's required to induce an EMF. I'm going to put this on the next test. What's required to produce an EMF, an electromotive force, or voltage? Induce. Well, let's start off with the first one. You're right. That's down. I usually put that number 3. First of all, you got to start off with a magnetic field. Got to have a conductor. This is to produce an electromotive force. We call it an EMF and voltage are interchangeable. So a lot of books in their formula they'll say E is equal to V times I, which I like because you got voltage using V, and you got what? E is equal to I times R. Somebody didn't call me out. So you got V over here and you solve for V. A lot of people don't like that. So if you ever see E, then this stands for electromotive force. Which is voltage. So you'll see that in books. So if you ever see that, they're talking about what? They're talking about voltage. So we're trying to induce one. We're trying to produce a voltage or an EMF with a magnet. So I got to have a magnetic field, I have a conductor, and I have to have motion. So I come over here and I saturate my transistor. A magnetic field builds up around this thing, causes the contact to close. Okay, so let's take the diode out. So this magnetic field is built out. The only way you get R in a DC relay is to have a lot of turns of fine wire. When I turn this transistor off, then that magnetic field comes collapsing back down into the coil and creates a really, really high voltage. So what I have here, hey, don't come here. You're not going to be here for that long. Everybody's got to make sure you have your mask on, right? So here I've got a coil. This would be simulating the relay. And what I'm going to do is, right now I'm going to see how much voltage it takes to turn on a gas bulb. This is a neon bulb. It takes a lot of voltage to turn them on. So I'm going to come up here. I got my meter on there. Right now I got 11 volts across the bulb. So right now I got 70 volts. It's still not turned on. So there's almost 86 volts. This thing, here we go, 90, 90, 90. So it just turned on. So it turns on a little over 100 volts. So if that light comes on, it means I'm getting at least 100 volts across it. So let's turn this down, all these 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 down. So what I'm going to do, here's a coil right here. And I'm going to charge that sucker up. So I'm going to take my coil and I'm going to hook it in parallel with the bulb. And I'm going to charge this sucker up to around 5 volts. And then I'm going to 3 volts, 3.7 volts. And I'm going to disconnect the power to the circuit, which is what I do when I turn off my relay. Here's the power to the circuit. Did y'all see the light bulb flash? So that means when I charge this thing up and I discharge this inductor right here, which is the relay coil, that sucker put out well over 100 volts, even though I'm only charging it up to what? Less than 4 volts. So what happens is there's a lot of turns of wire in that coil, and then when that magnetic field builds out, and I turn it off, it comes collapsing back into the coil. Now we have motion, now we have a magnetic field, and we got a lot of turns of wire. And it's going to generate what we call a counter EMF. So I'm going to charge it up, okay, discharge it, charge it up, discharge it. Now what I'm going to do is I'm putting this diode in here reverse bias. So what happens when the coil discharges, it's going to discharge through the diode. So here I'm going to charge it up again, discharge it, charge it up again, discharge it, charge it up again, discharge it. What don't you see anymore? So that's the purpose of the diode. It makes the coil discharge. So you charge it up with the magnetic field coming out, and then when it discharges it, the magnetic field comes in. So the EMF that it creates is in the opposite direction of the applied voltage. So what would happen if I didn't have that little diode? Well, what would happen if I didn't have that diode is that we have a breakover voltage right here. The breakover voltage for a 2N3904 is only 60 volts. So if I didn't have that diode in there, as soon as I turned that off, I'd pop my transistor just like that. So that means anytime you see it in a DC circuit, especially like PLCs, so most of your PLCs put out 24 volts, and you want your PLC to bring in a relay, you better put a diode across that port, or you're going to be replacing an output module sometime in the future. So we call this a flyback diode. They call it a counter EMF diode, that guy right there. And like I said, we can take you over to the Amatrol line, and they have a bunch of, we can take you over to the Festo line, and every relay you're going to see they have a what? They have a diode that's reverse bias across the port. So y'all understand what's going on. So that sucker puts out, what, over 100 volts when we discharge. So now I have no problem using a 3904, right? You understand that, because now if I was to put a 3904, it's got a breakover voltage of 60 volts, that sucker generates 90 volts or over 100 volts, I would wipe out that transistor. Maybe not on the first try, but eventually it's going to do what? It's going to get it.
As long as it's running, it's okay.
Yeah, it's only when the relay de-energizes.
It's when it de-energizes.
Yeah, de-energizes. That's when the coil, that's when it comes what? It comes collapsing back in and generates that big old high voltage.
See that nigga shoot across the circuit.
Huh?
Nigga shoot across the circuit and like close it back in.
Well, you know, transistors, devices can only block so much voltage. So you got all that voltage giving you all that push. So if you go out and buy a wall switch, it's going to be rated at two things. It's going to be rated at what? It's going to be rated at a voltage, and it's going to be rated at a current. Well, why do they rate it at a voltage? It's nothing but a switch. Well, that's the amount of voltage they guarantee that switch will be able to block when you open it up. Relay contacts are rated at a voltage. That's how much voltage they guarantee they can break. If you got enough push, you're going to arc across anything. You see lightning all the time. So if you got enough push, you're going to arc across almost anything. There's nothing that's got infinite resistance, right? You understand? Well, that's the same thing true with a transistor. If that sucker's sitting here dropping 60 volts and you push current back to it backwards, you're going to push it, you're going to pop that thing. So that's why diodes have what we call a PIV rating. So that's how much they can guarantee they can block when it's reverse bias. The transistors have what we call breakover voltages. So this would be called the voltage collector to emitter, and then they put an O out there with the base open. So if the base is open, you know the transistor's turned off, right? You understand? And if you exceed these breakover voltages, there's a high probability what? That solid state device is going to be damaged. So that's why I say on PLCs, we can take over there to every relay running off our 24 volt PLCs, and they'll have this counter EMF diode across the port. And we have suppression and stuff like that on AC, but especially on relay. So that's the purpose of the diode. So isn't that interesting? You see that thing charged up? It didn't turn on until we got what? About 100 volts on that thing. And when I charged that coil up and turned it off, I only charged it up to less than 4 volts. And when I turned it off, that thing came on. Okay, this one. This is the
calculations, with the 60. That's 6 volts. That's why I was working on calculating more with that. Because I guess by being instead of being instead of being 5.9, I'm doing it at 6 volts on the IC saturated. Coming up with the even 16 milliamps.
right, 16 milliamps. I'm sorry, so you're right. You didn't know.
So 16 milliamps divided into 30, the beta over here, and came up with
About 30.
Into 30.
Yeah, about,
16 million.
yeah. When we talk about microamps, it's not gonna make any difference with our
Okay. And then, the 5 volts, the,
4.3
yeah, 4.3 volts over 530
micro.
microamps equaling a 8.1.
Okay.
That's why I was saying right here, 8.1. Okay. Now I take that. No, 8.1. That's it.
Okay. 4.3 divided by 530 comes up to be 8.1. Yeah. It's like sometimes, guys. Sometimes you need to realize, you need to know when your answer is wrong, right? You understand that? So if I take a number here and divide it by a number, and if I come up with a number that's bigger than what I started off with, then I know it has to be wrong. It has to be wrong. And then of course you got to figure out. Then you can figure out what you're doing. So 4.3 divided by 530 or 533 times 10 to the negative 6 equals 8K. Yeah, 8.1 kilo ohms. There's not a standard value for that, right? So this one will be around that. So I can understand the confusion. I'll probably adjust this around so it don't come up right in the middle like that. So we don't have a. I think there's a couple of problems with the key on this. So what size would we use? What's below an 8.1K?
7.5.
That's the next thing down.
Next one up is 8.2.
I thought it was an 8K. But so that diode there, D1, or it's called a counter MF diode or flyback diode, and just to get rid of that counter MF that's generated when the thing collapses, right? We okay? All right, so let's figure this guy. So what do I know? I know this voltage right here, which is very, very, very important. I know this is going to be 3 volts. When this transistor here is turned off. So what you got to understand is when this guy right here turns on, this guy here is going to turn off. Y'all understand why? Because this guy here goes approximately 0 volts. I need at least 7 cents per volt to turn on Q2. So when Q1 is saturated, Q2 is off. So to get Q2 on, I got to turn Q1 off. And I still can't get the motor racer.
So you said it was 3 volts right at 8.
Yeah, A is given right here. Right here. It says the voltage at point A equals 3 volts when the first transistor is turned off. When the first transistor is turned on, it's equal to approximately 0, right? Understand?
Had the other equation.
Okay, so what do I know about R2? So VR2 is going to be equal to about 3 volts minus 0.7. So what's that going to be? 2.3. Alright, so I give you R3. R3 is given. We're trying to calculate R2 and R1. So, IC, the saturated IC is going to be equal to 12 volts divided by 1K, which equals 12 milliamps. So remember right now, this guy right here is off. So I can calculate IB now. So IB would be equal to 12 milliamps divided by 50. And we'll walk it 100. So what's IB equal to? Everybody okay so far? So what's 12 milli divided by 50?
140 micro.
140 microamps. Right, you okay? 240? That's okay. No big deal. I just say that to scratch out. Not be able to raise. So although R2 is going to need to drop 2.3 volts at 240 microamps. Somebody calculates out to me, 9.6. So what would we choose there?
If you round down, let's look at what 9.1.
What's that, 9.1? Okay. 9.17. This is why I don't want to charge you 8, right? Okay, so what about R1? So here's our two current paths. This guy right here. Here's one circuit. Of course, we know this guy here is going to drop about 0. Then we know our other current length is back to positive is this way. Sums of the voltage drops have to equal to the applied voltage. So we can give it a shot. So I know this guy here is going to drop around 3 volts. I'm sorry, 2.3 volts. I know this guy right here is going to drop 0.7. So how many volts does R1 got to drop? How many? 12. 3. Yeah, it's got to drop 9 volts. Kirchhoff voltage law says the sums of the voltage drops have to equal to the applied voltage. So when I said 3 volts, that was 3 volts after this resistor, right? You understand? So that means if I got 12 volts here, I come down here, I got 9, I got 3, then the sums of these has to equal to what? 12. Y'all understand that? Yes or no?
Give me a little review. You know, because
So I'm coming up here, I'm saying, okay, I got 12 volts right there. Let's just do a series circuit. I got this resistor and this resistor right here. I said, okay, right here I have 3 volts. I'm not even concerned about those other two. This is the measurement between what? Here in columns. So all your measurements are from there. So I measured 3 volts right there. So I know the sums of these two down here, since that's the ones I measured, has got to be equal to 3 volts. Of course. But I don't need to know that. I need to know I got 3 volts right there, I got 12 volts right there, I got 3 volts right here. So what is that resistor right here got to drop? Listen, 9 volts. So whose law are we using here? We're using Kirchhoff's voltage law, right? So here's a series loop right here, and I know this 12 volts has to be dropped in this loop right here. I know 2 of them. In fact, the 2.3 and the 7 is basically a new point because I gave y'all this right here. So that would be measured from here. So 9 volts at what current?
The IB, which is the 253 microamps.
253 or 240. It's going to give you about the same size. 253 is when we recalculated for the resistor we chose. So R1 would be equal to approximately 9 volts divided by 240 microamps, or you could have recalculated that according to the resistor that we had. But this would be close enough. So what do we get for R1?
35.6K.
35.6. Yeah, 33K. Okay.
So that's on the collector side of it, R3, right? Either one, R1 or the 3 are both on the collector side of it, correct?
Well, this is on the collector side, or this is on
Round down, and
Q2.
over here on collector, we round it up.
Yeah, but we're on the we're talking about what's required to saturate this thing. R3 we round. This is given though, so we're not rounding that. What we're working on is we're not even looking at Q1. We're looking at saturating Q2. Q1's not even in play yet. So on the base side of Q1, on the base side of Q2, we're going to round down. Understand? So you're looking at Q1 already, and we're not even we're trying to get Q2 saturated, right? Does that make sense? So that's a good question. So right now Q1 is off. So Q1 is off, Q2 is off. So okay, so we're coming up here and we're fixing to. So here we're given the resistor. So now I'm giving you the resistor. So guys, like I said, I can't erase. So what size are we? So write that down. We're using a 33K here, and we're using a watt here. Like I said, I can't get to my erase. In fact, the only resistor I need, the only one I need is this guy right here. So what's R1? What do we get for R1?
33.
Okay, so now we don't have to choose anything for R2, R1 because for Q1 because we calculated that. Okay, so over here I'm gonna put 12 volts over here. So I mean, this guy right here is going to drop 11.3. I know this guy right here, when Q1 turns on, is going to do what? It's going to, R1 now, instead of dropping 9 votes, it's going to drop 12 votes. Y'all understand that? But what we just did is we turned this guy on right there, which means that point right there goes to approximately 0 votes. This guy right here turns off. It has no base current. Now, this is the path that we're looking at. So R1 has to drop 12 votes. YC SAT will be equal to 12 divided by 33K. What does that give you? So did I expect you to work this one? No, but I wanted you to give it a what? Give it a shot. You know. So what's the saturated current required for people? What's that? I'm listening. 12 divided by 33K.
Yeah, 4 million.
4 million.
Yeah, on your text you got, just so you know.
I got 3.2 on the key.
I'm sorry, I got that wrong. I missed the 3.
Oh, you missed the 3. Okay.
It should be 3.6. Okay.
12 divided by 33. What'd y'all get? I didn't hear that. 3.3.
363.6.
We're away from this circuit over here, and what we've done is when Q1 turns off, then R1 has to drop 9 votes. When Q1 turns on, R1 has got to drop 12 votes. So we have 2 paths. So when this guy here is turned on, that's going to put our base voltage at around 0 votes. It's never going to be exactly 0, guys, but it's going to be close to it. That's why when we teach saturation, we teach less than a vote. So we say if voltage collector to emitter is less than a vote, we assume the transistor is saturated. If it's equal to VCC, we assume it's cut off. If it's between the two, we consider it to be in what we call the linear region, or the active region. So what we're doing now is we're trying to saturate Q1 so we can turn this guy here off. So we calculated the current. We know now this guy over here has got to drop 12 votes instead of 9 votes. And so we calculated the saturated collector current to be 12 divided by 33K, and what did we get?
363.6 micro.
363 or 364. 364 micro. Remember, we're controlling 12 milliamps over here. So that means R4 is going to have to be equal to approximately 11.3 divided by 364 micro. Wait, sorry. Let's get this in. IB, we got to calculate IB first. It's going to be equal to 364 micros divided by 50. So what do we get? 7.3 microamps. So I'm controlling 12 milliamps with 7.3 microamps, but we're going through two transistors. So this guy over here is going to be equal, R4 is going to be equal to 11.3 divided by 7.3 micro. This is going to be a big resistor. So what I want to make sure you understand is that look at the gain on this thing. What's on the left compared to what's on the right. So this is the transistor. The transistor gives us a current gain. So we control the size of the valve with the base current. Right? You understand that? It's just like the handle on your water, like we was talking about on your sink. There's no way in the world you can stop the flow of that water, then you need to call your water company. But you can't control it, but you get a mechanical advantage with the valve, right? You understand that? So it takes a lot less force to turn your water on. So you grab it a little thing with one hand, just twist it, right? You understand? Like our sinks down here, we can just do what? It's got a little handle on it that we just flip up and flip down because you get that mechanical advantage. But what we're doing here is we're getting an electrical advantage. A very small base current can control a proportionally larger collector current. So whatever that calculates out, that's okay. So 7.3, about 7.3 microamps is controlling 12 milliamps.
I guess you can go up the line with that too, correct?
Oh yeah.
You get the longer.
We could hook them. We could do things. So I might have one rated at 15 milliamps, and then I could come over here and take two of them and hook them in parallel and controlled by the same base. So I can come up here and do this, and then connect them together. And if this guy's rated at 15 milliamps, now I'm controlling 30 milliamps. So we can hook these in parallel. Very seldom in series. But to get so we can look at some power amps. I think I got a diagram of some power amps, and they have several of them hooked in parallel. They put a little feedback resistor in the base in the emitter to keep one from taking the load. Oh yeah, this is the name of the game. And even though we got all this, you got to understand, I can saturate them, I can cut them off, saturate them, cut them off. So that's digital, right? So I can take the output of a PLC here that either puts out 24 volts or 0 volts, and now I'm getting microamps out of my PLC, but I'm controlling a big load. Or that's what the PLC uses. So the PLC, everything inside the PLC, the programmable logic controller, is very low current, very low voltage, 5 volts. Usually inside the PLC we run on 5 volts. But how can they bring that to the outside world? Well, they bring it out to the outside world through a bipolar transistor. Through an optical coupler. So normally we have an optical coupler, which on the programming controller. And then over here we have a photodiode or phototransistor. And then over here, this guy here would be drawing a big transistor on that. The optical coupler allows things, all this noise and stuff that's generated in an industrial complex from getting into the electronics of the actual PLC. Okay, so this is another thing I wanted to show y'all. This is, we talked about constant current source. So I'm going to put 5 volts over here, and I'm going to say about 1.5 volts at 15 milliamps. So I'm going to come over here. This is going to put approximately 4.7 volts right there. Everybody understand that? So what size resistor would I get 15 milliamps to drop 4.75 volts? put 5 volts. No resistor here at all. I'm gonna put 5 volts right there. Well, that 5 volts, I've got to drop from here to here. I've got to drop what? I've got to drop 5 volts. We know we're going to drop about 7/10 of a volt right there, so that leaves 4.7 volts across that resistor right there. So I'm thinking around 4.3 across the resistor. I want 15 milliamps to drop. I want that resistor to drop 15 milliamps. I'm sorry, 4.3 volts to 15 milliamps, which is what's required by the LED. So everybody understand that? So what we did is we're calculating this series loop right here. So what size resistor would that be? What's that?
Is it like 15? You use 15 microamps divided
Not
by
microns, milliamps.
milliamps divided by 4.3. I got 3.4 microamps.
Now we're calculating R. So R is equal to V over I.
Oh, 286.
So 286. So if those such things are 286 ohm resistor. So it's up to you. If I go up, the LED would be dimmer. If I go down, the LED would be brighter. So I decided to go down. So what side? And then I chose the resistor that I had. So what goes? I'm going down. So what side am I going to use? No, I didn't have a 240. I don't have a 270. I got a 220. Now, if I had a 240, I would probably use a 240. If I had a 270, I'd probably use a 270. But I used what we have in our car scheme. So instead of 15 milliamps, it's going to be around 19 milliamps, which is okay. So right now, if this guy here is dropping 1.5 volts, this is 4.3, then how much is the transistor dropping? What would my voltage collector emitter be? Here, now we're working on this loop right here. I've got to have 12 volts dropped in this loop right here. So I got 4.3 on my bottom resistor. I've got 1.5 on my top resistor. On my diode. So how much is the transistor going to drop?
6.2.
Probably about 6.6 volts.
I got 6.2.
Yeah, well let's recalculate this too. So 4.3, which would be about right. Okay. So this is the circuit. So what would happen if I come in here and put another LED right there? So what would happen? First of all, what do we get right here?
6.2.
So what region is the transistor operating in? Is it saturated? Is it cut off? Or is it active? Is it equal to 12 volts? No. Is it less than 1 volt? No. So it's in the active region. So this sucker is acting like an electronically controlled rheostat. So what happens if I put another diode in there?
Would it decrease the BCE?
It would on the transistor, because the current is set by this resistor right here. That current says I'm going to let 19 milliamps flow. So I add another diode, VCC automatically changes. I add another diode, VCC automatically changes. I add another diode, VCC automatically changes, trying to maintain that 19 milliamps. So this is what we call a constant current switch, which which is really cool. So we can, this circuit, we could use to charge NiCad batteries, we could use to charge anything. So this is the actual circuit here. And what I did, this meter right here is measuring voltage collector to meter. So right now I have one diode on, and my transistor is dropping 5.37 volts. I'm going to come up here and move over to another diode. Notice now two diodes are lit about the same distance, but my transistor automatically did what? VCC automatically went down. Automatically, because we've got what we call a constant current source. I'm going to go over here and I'm going to light up another diode. VCC automatically went down to 1.3 volts. So we're in the what? We're in the active region. So what the transistor's doing is automatically changing its internal resistance to keep a constant current flow. I'm going to come over here and add another LED. Of course, we're at the limits. Now the transistor's saturated. Can't get any more out of it. Right? So if I come over here and add one more LED, they all cut off because now we're not getting enough current flow to the diodes. But see, this is a constant current source. I mean, y'all understand that. So what I can do is anything I need to have a constant current, I can do what? I can use a transistor. I set the current with a what? With an emitter resistor. So we call this emitter bias. So we're using what we call an emitter bias. And the transistor automatically compensates its resistance to try to keep that current flow. So that's a constant. This is not a saturated switch. These guys are really easy to design. You just do what? You take your voltage up here. You calculate what current you want to flow. You never, by the way, you don't want to ever. You're always going to put a load up here. If you don't put a load up here, then you'll run up the transistor. But yeah, I did. And you can see 1.5 volts a piece. I'm losing 5 right there. 1.5 volts a piece. We could probably run about 4 or 5 LEDs. So it's constant current. So if I've got like a NiCad battery, I can come up here and do what? Just put my battery in series right there, and it would charge at 15 milliamps. So you look at a NiCad battery or the specs, it would tell you like the charging current on it or lithium battery. Of course, you need to add a little more to that to automatically cut it off when it gets charged. So there's a circuit over there that's monitoring the voltage output on the battery. When it charges up to the required voltage, it automatically cuts it off. Except for your phone, right? So if you got your phone plugged in, the whole time it's plugged in, that little charger thing's up there. So guys, that's saturated switch and constant current sources. Any questions? Alright guys.
Will this last one that we did with 2 projects be on the test?
This one, no.
Yeah.
This one will not be on there. In fact, on the test, every circuit you have to do is going to be a bonus circuit.
Okay.
I mean, you got this, okay, but you need to know theta, you need to know what happens, you need to know, so what we're looking at from trying to figure out if you understand so you can troubleshoot.
And it's going to
Being able to design it's okay, huh?
One is going to be computer, one is going to be written. The test on Thursday.
No, we're doing away with the written part.
Okay.
So it's going to be all computer. So that's why when I put this on here, these will be bonus questions. We're looking at